Hello, I am Matthew and this is my submission of the Medical Electronics project. This project is about patching a biosignal processing circuit and studying how it works. The following block diagram is that of a biomedical signal processing system, the heartbeat acquisition system, and I will explain how it works next. So how the system works. The system consists of a microphone that picks up the heartbeat sound from a stethoscope's acoustic output, and a signal processing circuit processes the output signal of the microphone to drive a speaker. And finally, the speaker plays the sound. The biosignal processing circuit starts with a preamplifier that boosts weak signals. The amplified signals then pass to a power amplifier to increase its current, making it strong enough to drive a speaker. Hence, the main goal of the project is to analyze, interpret, and test the signal processing circuit within a biomedical signal processing system. So now this is the full schematic of the project. To make things simpler, I will label TP1 to TP2 as stage 1, TP2 to TP3 as stage 2, TP3 to TP4 as stage 3, and TP4 to TP5 as stage 4. And now this is my circuit. Okay, now I will explain stage 1. Firstly, we need to know that op-amps are differential amplifiers as they amplify the difference between inverting and non-inverting inputs. Stage 1 is the preamplifier and it amplifies the signal level of a transducer output. It does so by enhancing the level of an electrical signal to reach the minimum level for further amplification. For example, it takes microphone level signals and amplifies it to line level, which is the standard used in recording systems. However, we need to know that stage 1 also only provides a voltage gain between 10 mV and 1 volt and does not provide a current. So now this is stage 1 schematic and I will be explaining it. Firstly, IC1 is a dual low noise JFET op-amp, also known as ICTL072. It is a fixed gain, closed loop non-inverting op-amp, and capacitor C1 is an input coupling capacitor that blocks DC offset and passes AC signals. Resistors R5 and R6 make up a voltage divider, providing half of the voltage for the op-amp to work in single supply mode and creates a virtual ground. Resistors R2, R3, and capacitor C2, C3 form a passband filter which passes frequencies within a range and attenuates anything above or below. The passband gain is 1 plus 220 kiloohms over 10 kiloohms, which is equal to 23. The frequency range for this system will be 16 Hz to 1 kHz. Capacitor C4 is an output coupling capacitor and it does the same thing as capacitor C1. If DC offset is amplified, it creates larger output offset, pushing the output towards one of the rails and reducing headroom, thus cutting the waveform. Okay, now this is the table for stage 1. Based on this table, we can see that when testing our circuit, our gain should increase to about 22.5 at 100 Hz before dropping. And for the graph of stage 1, we can see from the graph, it shows that at 100 Hz, the voltage gain is 27 decibels. From this, we can find the lower and upper cutoff frequency by plotting a negative 3 decibel line and finding out the frequency that correlates with the intersection point between the line and the graph. Based on the graph, the lower frequency is 16 Hz and the higher frequency is 1.2 kHz. The bandwidth is then calculated by finding the difference between the two frequencies and is 1.2 kHz minus 16 Hz, which is equal to 1084 Hz. Now this is my recordings for stage 1. To measure for stage 1, we will connect probe 1 to TP1 and probe 2 to TP2. The output value at TP2 would then be about 2.6 volts. This occurs when the function gen is set to 15 Hz 200 mV peak to peak. Now, when changing to 200 Hz, we would then be able to realize that the output value has increased to 4.12 volts. Next, we will change the frequency to 1 kHz. Now, the output then decreases down to about 3.08 volts. Lastly, we would change the frequency to 2 kHz. This shows the output reduces further down to about 2.24 volts. Okay, now I will explain stage 2. Stage 2 is a negative feedback loop amplifier and it adjusts the gain of the op-amp IC1B by adjusting the resistance in the feedback loop. Negative feedback occurs when a portion of the output voltage is fed back into the inverting input of the op-amp at 180 degrees out of phase. Stage 2 also has a trimmer that controls the feedback signal, which can reduce or increase the overall gain of the amplifier, hence allowing it to tune the gain. This is the schematic for stage 2. IC1B shares the same IC TL072 as stage 1, and P1 is the trimmer that adjusts resistance within the circuit. Resistors R9 and R10 act as a voltage divider that helps the op-amp work at single supply mode, and they also act as a level shifter to prevent the output from clipping. The waveform will then be reduced or amplified when the trimmer is turned, and eventually at some points it will either be flat or saturated. Now I will explain how a level shifter works. We can see that the single supply mode causes the negative side of the waveform to be cut if a level shifter is not used. So, by using a level shifter with two resistors, we can scale down the voltage based on the formula V out equals to V in times R2 over R2 plus R1. And we can see in the graph drawn that when there is a level shifter, we can shift the whole waveform upwards to prevent the cutting of the negative side of the waveform. Now this is my video recordings for stage 2. To record for stage 2, we will leave the test probe 2 at TP2 and move test probe 1 to TP3. We can see that the output would be 5.6 volts. Now, when turning the trimmer right, the sine wave would increase until the output voltage is too high and the wave cuts off at the top. And by turning the trimmer left, the sine wave would decrease until the trimmer is flat. Now, I will explain stage 3. Stage 3 is a silent key second order low pass filter made out of two low pass RC networks. This filter is used to remove high frequency noise from biological signals while keeping the signal of interest. Low pass filters allow low frequencies to pass and attenuates high frequencies. The bandwidth of a low pass filter coincides with its cutoff frequency as FL equals to 0 Hz, FH equals to FC, the bandwidth equals to FH minus FL, which equals to FC minus FL, and since FL equals to 0, hence bandwidth equals to cutoff frequency. The lowest frequency that can pass is 0 Hz. The cutoff frequency of a second order unity gain Butterworth filter can be calculated by the formula as shown here, where RA, RB, CA, and CB are the frequency selective network. This is the schematic for stage 3. We can see that stage 3 uses a different TL072 IC and it is a second order as there are two RC networks. Capacitor C5 is an input coupling capacitor and resistors R11 and R12 is a voltage divider that acts as a single supply mode for the IC. They are also level shifters to ensure no output is clipped. Capacitor C7 provides feedback for shaping the response near the edge of the passband and only allows low frequencies to pass through. Capacitor C8 is an output coupling capacitor. From the previous formula, FC is calculated using resistors R7, R8 and capacitors C6 and C7 and is about 996 Hz. This is the table for stage 3. This table can give us a rough idea at what frequency the gain would drop. However, this table is not accurate to our readings as this table is based on the setting of the function generator to a 20 Hz sine wave and amplitude of 5 VPP, whereas our function gen used in the recording later is set to an amplitude of 200 mV peak to peak. Previous stages would also affect our readings here. Hence, we can only use this table to get a rough idea of what our reading should look like. Now this is the graph for stage 3. Based off the table previously, we can see that when frequency is below 500 Hz, the filter is at unity gain, but frequencies above 500 will cause the gain and output voltage to drop. Thus, our recordings should have roughly the same type of graph shown here. We can also find the bandwidth by drawing a negative 3 decibel line and finding out the cutoff frequency, and since bandwidth equals to the cutoff frequency, hence we can find the bandwidth there. Now this is my video recordings for stage 3. To record for stage 3, we will leave test probe 1 at TP3 and connect test probe 2 to TP4. The output voltage is then measured at about 4.4 volts. This occurs when the function gen is set to 200 Hz and 200 mV peak to peak. Next, we will change the frequency to 1 kHz and the output shown would decrease to about 1.8 volts. Lastly, we would change the frequency to 2 kHz and the output will continue to decrease to about 424 mV. This shows that the outputs measured follow the graph as shown previously and the readings are accurate. Now, for stage 4. Stage 4 is an audio power amplifier that drives a speaker and is designed in a single supply mode, so no additional voltage divider is needed. Stage 4 drives current to power the speaker and is designed for AC audio signals as DC can shift operating point and cause distortion. Stage 4 also has a trimmer to adjust the gain of the amplifier and allows fine-tuning of the final output. This is the schematic for stage 4. IC3 is ICLM386N and as stated before is an audio amplifier. T2 is the trimmer. Capacitor C15 helps filter out frequencies above 40 kHz. Without C15, the output waveform will be slightly unstable. Capacitor C13 is the final output coupling capacitor. When input enters trimmer, pin E has full amplitude while pins A and S have zero amplitude. Now this is the video recording for stage 4. To record for stage 4, we would leave test probe 2 at TP4 and connect test probe 1 to TP5. Now we can see that the output voltage is about 7 volts when the trimmer is at the utmost right. By turning the trimmer to the left, we can see that the amplitude of the sine wave decreases until it is flat. And when turning the trimmer back to the right, we can see that the amplitude increases until it reaches the maximum output voltage of about 7 volts. Lastly, this is the video of my full working circuit. To record for the final stage, we will connect test probe 1 to TP1 and test probe 2 to TP5. We can also see that the maximum output voltage before the sine wave cuts will be about 7 volts. Now, by adjusting trimmer 1, we can see that it adjusts the overall gain of the amplifier, and when it is turned to the right too much, the top of the sine wave would be cut. Now, we will see that trimmer 2 allows for fine-tuning of the final output, and when it is turned to the utmost right, the output would not go past what was set in trimmer 1.